Okay, so gallium is quite an unusual metal. First of all, it melts at a very low temperature, only about 30 degrees Celsius, and it is less dense as a solid than it is as a liquid. So it floats on top of itself, very similar to water, which we'll explain soon. Another weirdness of this metal is it's actually brittle and not malleable, so you can actually snap it, as you can see here, rather than it bending. And so this doesn't match a metals. Gallium is a metal, though. It's left of the magic line of semi-metals. And it does have properties of a metal. So I don't have a recording, but it is making a nice tingling sound, the little metal pieces in the beaker. Um, and it does conduct heat and electricity, which means it's got free electrons moving. And it's also shiny, as you can see, and that's all in line with electronic band gap theory. If you want to look at more details onto why metals are shiny and conduct electricity, um, and so the answer to this is because the structure of gallium is actually internally inconsistent, and when you actually try and get the structure of it using X-ray diffraction, that means it's a very messy thing to try and work out. And the X-ray diffraction method itself actually alters it. So they can't really get a straight answer on what gallium actually is. So if you look at all the research out there, it's quite a mess. It's quite a detective work. There's lots and lots of clues. And so there's different research articles, some taking a theoretical orbital prediction basis, some looking at how gallium interacts with other compounds, especially iodine, and they piece together what they think is going on, which makes a lot of sense. It's also fascinating that in the modern age, we don't know simple things like what's the structure of gallium. Um, but we have got a reasonably good idea from taking many, many different bits of evidence and trying to piece it together, which is often how chemistry works anyway. Um, and so to the left of the periodic table, you've got zinc, which is a standard metal. It's closely packed together in a metallic lattice, so they've got strong metallic bonds, high melting boiling point. To the right, even though it's a semi-metal, it is a lattice of covalent bonds forming a covalent network solid, so that also has high melting boiling point. So why on earth does gallium buck the trend? It's a metal and it is what it is. So the current understanding is that those free single 4p electrons in those 4p orbitals, they form covalent dimers. And so gallium is like a whole heap of gallium, sort of diatomic molecules that are stacked up to form the metal. And so it's got this part covalent bond structure to it and part metallic bond structure to it. And so uh, in reality, everything's just positive attracted to negative, and we've just applied these thoughts to it, these labels to it. And so that's why it acts a little bit like water, because water has hydrogen bonds that are less dense and sort of form these spaces. And then when you increase the kinetic energy, you break those hydrogen bonds and it's more dense and it sinks. And so the solid floats on the liquid. Uh, Gallium is very similar as well. So when you increase the kinetic energy, you sort of break these weak covalent dimer bonds, and the dimers break, and it becomes more dense. And so the liquid is more dense, and the solid will float on top of the liquid, just like water. So that is very rare and unusual. So the covalent bonds in the solid also account for the anomalies in the galvanic metal, and so covalent ionic are brittle, and so it is brittle as a solid, and it's not actually malleable. And the spaces, because of those poor packing of those dimers, the positive and negative forces are not close to each other, and so there are spaces there. So the metallic bond is very, very weak, and so that explains why the boiling point is very low. Dimers themselves will only have weak London dispersion forces, but this is a packing of the dimers, so there's still metallic bonding with the packing, even though there's this internal structure around it as well. So it is all just positive attracted to negative, and so the port packing of the dimers means there's greater distance; they're not close to each other, and so the metallic bonds are much weaker. So always positive attracted to negative. Three-dimensional packing of the positive and negative affects its distances. You should note that from your periodic table lessons as well. And so that's why the melting point is much lower. I hope that explains all the weird properties of gallium.